basically integration of neural networks into all sort of sub-algorithms within ICM, and time permitting, maybe also highlight a few recent other features. Probably a few in the audience need, to be convinced about us experiencing a period of huge growth in neural network computing, which is fueled by a lot of data, in our field, protein structures, chemical biology, also quantum chemically calculated data. And on the other hand, the advancements in neural network architecture, starting with convolutional networks in image recognition, and then more complex architectures such as denoising networks, transformers in language learning, etc., etc., etc. And all of this, of course, wouldn't be possible without GPUs that allow us to crunch all the data through the complex networks. Now, closer to us here at Molsoft, a few years ago, we decided to try and integrate neural networks into ICM, not so much because of all the noise around it, but we really felt that there are great advantages of neural networks over other machine learning methods, in particular in terms of flexibility, absolutely unique flexibility of neural networks in terms of their adaptations to various inputs, 2D images, 3D graphs, whatnot. You can find an architecture that would take it in. You can create architectures that can reflect certain, underlying processes within the data and capture them better than a generic machine learning method. And you can make networks that yield all sorts of interesting outputs as well, create multitask models. For example, we have in Molscreen a model of 240 kinases in one, and it's not just a sum of models, but they actually sort of cooperate in a transfer learning fashion, improve each other, and it's much easier to deploy them separate networks or other methods. So with that in mind, we connected ICM or linked it with MXNet, which is a platform or a framework, I would say, that implements all sort of inner workings of neural networks that are necessary to train them and deploy. And this is an open source, basically C++ library, so we could directly connect to it and train from ICM and then use models straight from our various simulation algorithms within ICM. Once we had it integrated, we started to try and apply it to all sorts of applications, starting with, of course, activity models, but also prediction of properties and sort of more foundational models that are used within our algorithm for simulations, for example, atomic parameters like charges or scoring or models of conformational behavior. And that's what sort of I would like to talk about in this most of this talk. Later on, we are currently also working on some interesting new things like generation of structures. There are some early successes there, but it's maybe too early to present today. We work on also networks that would do some sort of structure analysis, feature detection, etc., etc. Now, once we had this MXNet foundation integrated, we quickly realized that we want to add to it something that would allow us to more efficiently handle our most common input, which is chemical structures. As you probably realize, chemical structures are kind of problematic as an input for machine learning in general. The machine learning algorithms, they like fixed length vectors essentially. And traditionally, you would have some sort of pre-embedding where you apply calculation of some kind of descriptors or fingerprints. Probably most popular right now are the CFPs. that makes the molecule into that vector, generic sort of fixed length vector, and that this is fed into machine learning. Convenient in a way for the machine learning, but you always end up, well, restricted with that initial step. Whatever it does embed well, it does, and then you get good results in that sense. But if something is not embedded well or embedded in such a convoluted way that it's difficult to decipher on the side of a machine learning algorithm, it will always restrict your performance. So we wanted to have a network that could work directly on chemical structure, and a class of such networks is graph convolutional neural networks that operate on graphs, and chemical structure is a graph essentially. So if you think of molecule as a graph, the atoms are nodes connected by bonds, and you can sort of set up those vectors of well, neurons or embeddings on each atom, and then they could interact with each other, pass messages. Another name for this kind of networks is message passing networks. So those could then directly operate on molecular structures, which I think is very interesting ability, because it can capture everything that potentially that there is in the chemical structure. And on the output, you could yield either overall properties via some sort of pooling, or you can get actually atomic and bond-based properties, which is also very useful if you are intending to use it as, you know, input or part of some sort of molecular mechanics calculation or other such things. Well, the most sort of naturally fitting application for this type of networks is probably partial charges. That was one of the first models we played with after implementing the graph convolutional layers, which was sort of an addition to what MXNet normally has in it. We could actually get very good predictions. You see this near perfect correlation. You would rarely see it otherwise in any kind of real world situation other than, well, charge prediction as it happens. We trained the model on 130,000 molecules. This is from a paper where they originally did this similar type of modeling, but using random forests. They calculated charges using DFT and then DDEC algorithm by Thomas Mans, and trained on those. We used that set in our own work here, and all the metrics are excellent, I would say. And RMSE, for example, is about hundreds of electron charge in near perfect, and significantly better actually what is reported for RF model. RF model is also way bigger. It takes 6 gigabytes. So just loading it takes a while, right? Our neural network is 86 gigabyte in size, the parameters of the model. So this was quite encouraging. When we looked also at how GCNNs could work for activity predictions, hERG is one target that is often interesting, you know, for the off-target testing and elimination of problems with this important off-target that lead to side effects. So we tried to train the model just using the convolutions that I already mentioned. Then we added more complex convolutions that propagate farther along the graph, and eventually arrived at this model that is quite good, I believe, about 0.7 R square on cross-validation set. It was trained on compounds from Campbell. GCNN ensemble outperformed other models, CFP-based, for example. And it was predictive both globally and locally. On the plot, you can see these little red boxes. These are actually compounds from real projects where one project where a series of compounds were made that some were tested actually. And the numbers fall, well, pretty well. I mean, they are slightly higher than the line, but diagonal, but you know, eventually even different measurement methods may give quite significant differences in hERG measurements. So that's quite encouraging, I think, too. Now, I will spend a while on the next model, which was about prediction of torsion profiles. Why torsion profiles were, it's a pretty common problem in molecular modeling or design, where you see some model of, let's say, ligand in a binding site or otherwise, and you want to understand whether it's in a relaxed state, let's say, the torsions are in the favorable regions or not. And this sort of evaluation normally is accomplished by either calculations with quantum chemistry. So you would do a torsion profile by scanning rotations around the bond, which is quite expensive computationally and kind of complex to set up and perform. You need to prepare some nice model molecule, do the scan. Sometimes it doesn't converge, etc., etc. The alternative commonly used is database search. So you look in a database of crystal structures of small molecules and do some statistics. You need to construct the query in a way that sort of mimics your molecule of interest, etc. And again, kind of complicated. And so we were interested in whether we can do better with neural networks. And yes, because, well, torsion profiles are also interesting for us in particular, because what we do, as Ruben talked about, things in internal coordinates, primarily torsions, right? So you really do want to know how a torsion in an arbitrary organic molecule might behave, that could help us with sampling and scoring, etc. So we worked on that for quite a while, and actually eventually published a paper a few months ago on convolutional neural net model for torsion profiles. The way we went about it was to construct this pretty sophisticated network architecture. Took a few iterations to arrive at this structure of the network. We went beyond those simple convolutions that I described previously. We had to have this convolutions that would provide directional data flow, because basically, well, the way torsions behave doesn't get reflected well if you just collect data sort of uniformly from all directions, because well, one side of the torsion affects things differently than the other. Let's say, I mean, they're not interchangeable. So you want this directional flow. You also want to somehow incorporate things like chirality, and that required us to introduce something similar to what is now known as attention in transformer networks, for example, where you basically weight certain signals according to some parameter, and in our case, these are the phase angles around the rotatable bond. So that all led to this structure of the network that is better described in the paper. I can't really go through every layer here, given the time. So we next trained this model using crystallography open database. This is a very nice project, primarily by, I think, Lithuanian group that started, I don't know, maybe 15 years ago or so, collecting publicly open collection of small molecule crystals that now provides a good alternative to the known, well, sort of privatized collection of public structures from a known company. Anyway, we extracted from that collection about 60,000 structures, primarily based on the elemental composition, and well, also some size, and filtered out some pathological cases. Anyway, 60,000 training set. I just wanted to mention that the COD is available within ICM. As a side note, you can go to a search bar and find it under crystallography open database, do a query, and get a series of structures. You can review their lattice arrangements, and this is even in the free ICM browser. So if you don't know about it, please try. So the model, once we had trained it, we first explored whether it reproduces sort of textbook cases. In this table, there is a number of different structures. At the top, cases that you could basically just guess from things like hybridization, and it does reproduce, the flatness of, let's say, amides and other similar molecules. But then if you start looking towards the middle, we tested some cases, for example, where there is some steric restrictions from more distant atom, and it removes peaks that would be otherwise there. If you have two orthosubstituents, then both peaks disappear and they move into like 90-degree region, for example, for this molecule. The model also captures things like hydrogen bonding, internal hydrogen bonding that stabilizes certain configurations, like this peak is wide, here it becomes narrow because of hydrogen bond. Here, this is donor and acceptor, this is only an acceptor, so the peaks shift again. Lots of these kind of things, just to show that, the network really grasps all these little features, not just locally, but also more remotely, and more sort of unusual things. For example, at the bottom, you can see that this is an example of gauche, so-called gauche effect, the chain that sort of naively or intuitively you would think would prefer being in trans conformation is actually preferring gauche, and that's again captured by the model. This is an interesting effect where oxygen and sulfur actually attract each other at certain angles of approach, which is again kind of counterintuitive. Sulfur is a large atom, and you would probably, I would expect that oxygen would be more on the other side rather than here, because nitrogen is smaller than sulfur, but there is this attraction. There's a couple of papers in the literature, they even correct for fields specifically to capture this. Again, the model did extract that information in training. It also captures effects of chirality. So for instance, I mentioned that phase attention kind of feature, and without that we would predict a symmetric profile for this molecule, which is this blocked amino acid essentially. Once you introduce this type of network layer, you get a symmetric profile as expected. Since the blocked amino acid, you can think of this profile as just a projection of Ramachandran plot onto the phi axis, right? So everything is here, there's almost nothing on the right side, which is correct. It also understands rings. So for example, here we have a aliphatic chain, but in a ring, right? So that of course kills the 180-degree peak that would be otherwise there. Normally you have 3 peaks for this kind of torsions, and then there is also a distinction between these 2 angles, because one results in equatorial versus axial orientation of the substituent, and equatorial is preferred due to steric restriction. So all correct again. So that was sort of a review on case-by-case basis. Now we also compared our profiles to a larger set of just DFT calculated profiles. Last year there was a publication on a pretty close subject where I think it's a Pfizer group. They actually calculated a large training set of DFT energy profiles for torsions and trained their model on that. Unfortunately, the whole training set is not available, but a subset of 500 molecules was made publicly available. So we took it and compared to our predicted profiles. And we see that indeed, our profiles and their profiles in most cases correlate quite well, sort of in the way that you see it here at the top. We transformed our probabilities into energies using the Boltzmann relationship, assuming that there is a quasi-Boltzmann distribution there. In some cases, maybe the scale would differ, because again, the Boltzmann assumption is kind of not really exact here. We don't know the effective temperature of crystal environment, right? But anyway, the profile is still, matching largely in terms of shape and location of minima. There were cases where there was significant divergence, but when we look at them, a lot of them trace back to the fact that some of their model molecules had more than one flexible torsion, which actually results in some strange artifacts once you start doing those energy calculations and screens, scans, because, for example, if there are some hydrogen bonds potentially forming, then the molecule at some point would experience this sort of collapse where a hydrogen bond suddenly forms during minimization, and then the profile calculated by DFT has this weird behaviors, which are probably not very meaningful or useful practically. So I think our profile is actually better in a way than what DFT generates here. Now, how can you access this in ICM? Well, it's used now in the interactive sort of mode, where if you just use a rotation tool in the 3D window, this kind of profile will show up, and the little red dot will slide along it as you rotate. The rings on torsions, when you label torsions, they are also colored according to the model, so that the red ones are those that have suspicious angles, and green ones are good. If you don't have ICM, you can also try it just online. We have a free interactive service there where you can draw a molecule, and then similar to here, just rotate the torsion and watch how the energy changes on that profile in the corner.
Max, we're coming up to 5 minutes left.
Oh, okay. I need to accelerate. Thank you. So now the other application is more sort of within our internal algorithms, and this is for conformer generation. So the standard procedure that we have for creating conformer libraries, for example, for RIDE, is in constant script, and this is based on Monte Carlo with gradient minimization. Now, how does the non-torsion model help here? Well, we implemented a variant of the algorithm that does a prediction for the molecule and then uses those profiles to sample more efficiently. How does it do it? Well, let's first just review this little case here. This is a molecule of trimethylprim, and if you predict all the profiles, you would see that, for example, for these two torsions, you only have one peak, so then basically you probably don't need to sample it, right? For this torsion, that predicts those 90-degree peaks, which are sort of not what you would expect from just the type of the torsion, but of course they are correct because of the steric repulsions here. And the other profiles are also having those peaks. Here, those peaks then can be combined in AI-assisted sampling. So we basically predict all torsion profiles with an torsion, extract the peaks, and then systematically search for those peaks. The search can be restricted to a combination of peaks that have some preset minimum probability. We tested this on a platinum benchmark. This is a benchmark that was applied to evaluate a variety of algorithms like omega, etc. And we find that it's quite performed quite well. Here is a summary plot, sort of how far we get, how close we get to a bioactive conformer with our conformers. And you can see that up to about 10 rotatable buoyants on average, we find in most cases something within 1 or perhaps 2 angstroms of that bioactive conformer. It's also requiring only a limited number of conformers. As it turns out, we get results similar to other methods at 16 conformers per molecule, as opposed to like 30 plus for the methods that are evaluated in a paper. And it's about 3 times faster than our standard MC protocol. So there is quite a benefit there. RTCN, well, I'm running out of time, right? RTCNN, well, that's the other network. I'll just run through really quickly that is used for scoring, right? We try to sort of incorporate physics ideas into designing this network. So using those convolutions that are on the ligand and receptor side, first evaluate the interaction properties of atoms, and then the other convolution then actually sort of mimics the actual interactions at close distances between ligand and receptor atoms. We trained it on a training set of docked poses for ligands that are small molecules and peptides, correct and decoys about 70,000 structures. It's kind of a learning curve, how the training proceeds. And here the evaluation results using CASF benchmark pose prediction, pretty good. This is screening, enhancement factors, enrichment factors. Average enrichment factors you see quite a bit higher than typical for other methods. I have to note here that we did check whether this is overtraining by excluding receptors that have same cis-prod ID from the benchmark that corresponded to something in our training set, and there is no drop in enrichments. This actually is a little bit higher, but I'm pretty sure it's just, well, some noise, but definitely no loss in accuracy. This is used now within ICM as we basically apply it as a second score in consensus scoring schemes. We use it for visualization to color molecules. We use it also because it's really fast, much faster than our regular score for ultra high throughput processing. I think Eugene will talk about it more. Some caveats to keep in mind about RTCN is that there's no strain in it, unlike the normal score, so it doesn't really understand if the molecule is strained. And it has pretty weak clash penalties. Normally, our docking produces reasonably unclashed structures, but if there is some kind of constraint situation, that might be an issue. So need to keep in mind that clashes are not really penalized heavily with this score. Here's how the second score helps when you combine it with a physical score. A few different schemes explored, just combining as a sum by consensus, so, you know, cutting on both scores and then cutting sort of in this more complex pattern to keep the most interesting part of the distribution. 10 receptors, you can see that across the whole panel, we have, you know, from moderate to pretty substantial boost for any of the schemes. I don't see a particular, you know, preference for one approach versus the other, but always pretty much we get better with consensus scoring in some form. Here it's the limit of, you know, this test, so you cannot really grow up much higher. And then, well, just really rapidly, features that I wanted to highlight. Improvements in peptide simulations and docking. We added, you know, ability to quickly build and simulate non-natural dipeptides, stapled peptides. You know, we can redock quite complex structures there. We can also plot them in this, I think, fairly nice way, compact way. We added MD through OpenMM library. Now you can run directly, you know, MD simulation within ICM through command line, or, you know, through a script that encapsulates basic preparations. We had the tools also to analyze those the results of simulations, just some simple things like interatomic distances, RMSDs, etc., contact areas, and such. We added recently product simulation protocol, builds models of products, and here I wanted to show that we can kind of combine the two tools to actually, you know, build some models first and then refine them with MD. We see, like, at least especially for poses that are closer to, you know, like at 6 angstroms, we can get down to 2 angstroms almost in every trajectory. This is roughly how it looks like. You know, the pose is sort of roughly there, but really shifts towards accurate answer upon simulation. So this is a summary, and well, thank you.
Thank you very much, Max. We have some questions. Some of them sort of were